Now we're going to look at a general, very typical two-dimensional motion problem that involves constant acceleration. The key to your problem-solving analysis is definitely the points 1 and 2 that are made here. You always want to separate your analysis out into x direction and y direction. Do your calculations separately, and then combine your x and y answers at the end using vector additions. So let's see how this plays out in this particular problem. We are told that a moderate wind accelerates a pebble over a horizontal xy plane with a constant acceleration given by 5 meters per second squared in the x direction, positive 5, and positive 7 meters per second squared in the y direction. We are also told at time t equals 0, the velocity is 4 meters per second in the x direction only. So we are given the acceleration in the x direction, the initial velocity in the x direction, the acceleration in the y direction, and since we are told it only has 4 meters per second in the x direction, we know the initial velocity in the y direction is 0. And what's more is that we are told that the object is being displaced 12 meters parallel to the x-axis, so we know delta x is positive 12 meters. Very important before you begin to even think about which equations to use, how do I solve this, is to get down the givens in the problem. Now, as it says here, time, of course, does not have an x or y axis subscript with it. Time is the same when the object is both at its x position and its y position. So, as it says, we're going to start here with our analysis, and there is no magic formula way for you to know which of the constant acceleration equations to start with. In general, if you're not given time information in the problem, which we are not, I will try to use the third constant acceleration equation, v final squared equals v initial squared plus 2a delta x, which I do here in the x direction, to calculate the final velocity after the object has moved 12 in the x direction with an acceleration of plus 5. So we have our final velocity in the x direction. All right, so let's go over to the y direction. Now, again, we don't have the y direction, we don't have time, so I would start here with this equation. We do not have, we have v final, we're looking for v final in the y direction. V initial in the y direction is 0, so that's okay. But we do not have the delta y, okay? So let's go to our next equation. We have v final equals v initial plus acceleration times time. So again, we don't have time, so we have a choice. We have to try to either solve for delta y or t. Here, since I'm given v final in the x direction, I can use my x information to find out how long it took to move in that direction. And in this case, as you can see, it took 1.53 seconds. Time is the same for both. So when it has moved 12 meters in the x direction, it has taken 1.53 seconds, and I will plug that back in to my equation here, right? So that's where this equation came from. The initial in the y direction is 0. Acceleration in the y direction is plus 7, and my time is 1.53. So now I have my velocity in the y direction as well. So I will do as it says in step 2, combine the x and y information. So my v final in the x direction is the 11.7. My v final in the y direction is the positive 10. Tip to tail, I get my v final is 15.8, and my theta from inverse tan is 42.6. So you can see how everything we've done in chapter 2 and 3 have formed the building blocks for what we are doing here in chapter 4. And I hope you are beginning to gain confidence that things are falling into place, and we are seeing how this two-dimensional world behaves. So I took my erasures off. Pause the video if you need to. Make sure you get all of your annotations in and understand how this solution works.